Right. Good morning, everyone. Welcome to the first VISS seminar this term. It's our great pleasure to have Professor Vivek Borkar with us. Professor Borkar is one of the pioneers of stochastic control and reinforcement learning and have done foundational work in topics varying from convex analytic methods for MDPs, analysis of single and multi-timescale stochastic approximation algorithms, which are the basis of the proof techniques of all reinforcement learning techniques. Today, he's going to be talking about some very recent work on reinforcement learning for non-Markovian environments, and we very much look forward to your talk.
Okay. Thank you, Aditya, for your invitation. Yeah, so this is actually this kind of a rambling kind of a talk, and there are a few results and a lot of philosophizing, more or less. And it started with some work of Van Roy, which Ben Van Roy in Stanford, with one of my students, former student working with him, pointed out to me, and I found it very interesting. In particular, the formulation itself. So he looked at reinforcement learning for a general process, not necessarily a priori known to be a Markov chain, and he came up with certain sort of framework for it. So you observe some process in some space scripto which you want to control. Sorry. And you have to postulate this following object. There's an agent state Sn taking values in the state space S and a control sequence Un taking values in an action space U. And the state is the agent state is basically given recursively. As Sn plus 1 is a function of Sn, previous state, the control, and what you observe. And also there's a corresponding reward, which is per stage reward, which you receive at each time. And then he derives a regret bound for the reward relative to the best possible. And then he refined it further with another sort of theme, with the kind of more added more structure to it, so to say. So the Xn, the agent state Xn is now 3 tuples, Zn, Sn, and An, where Zn is what he calls algorithmic state representing the data cached by the agent for computational purposes. Sn is situational state, which captures the agent's summary of the current situation. N is what he calls epistemic state, that captures the agent's current knowledge of the environment. And sin plus 1 is some independent random variable that allows for randomized updates, which I actually have just without loss of generality assumed to be a random variable taking values in the closed interval 0, 1. Of course, without loss of generalities, if you don't impose any regularity, if you want some, I'm just invoking the isomorphism theorem for Borel spaces, but that's just measurable isomorphism. So if you impose some conditions, then you cannot arbitrarily just plug in 0 and value. But for my purposes, this is good enough. And as usual, you have this process of history, which is everything you have observed at time n, which in this case is your observation process of POM and your control UM up to time n. And then again, there's a reward, which history-dependent reward, which also depends, of course, on control and your observation. And he establishes a regret bound using, uses a lot of information theoretic techniques for this, but this I'm just mentioning in passing because I don't derive any regret here. It's the objective is somewhat different. Just to kind of primarily to make some connections with existing notions in classical stochastic control and point out some possibilities. Okay, so here's a list of what I propose to do. So to start with, I'll stick to the first setup, which is just the simpler, the less elaborate setup of the first paper of Ben Van Roy. And also we take the observation process to evolve from time minus infinity, and so I'll also assume mention it later that it's stationary, and that simplifies things a lot. So it would be good to go beyond that. I'll mention the possibilities a little later. There's something which are much simpler if you simply work with stationary. So these superscripts will denote the semi-infinite sequences up to time n. U sub n will denote the, so this O sub n is of course the observed process till n. U sub n is the control up to n, and the history is then the pair O sub n, U sub n. And I'll drop the explicit randomization sign plus one and just assume that un can be randomized controls. So script P is always the space of probability measure on some Polish space. And I'll take the agent states, the state space for the agent state Sn, the control space, and the space where observations come from to be finite states. And the main contribution is to pin down the error caused by potential non-Markovianity of the observation process. If you just plug in blindly the standard Q learning algorithm. And this leads to an alternative, I mean, it's kind of an alternative performance criteria, but it leads to kind of motivates approximating certain conditional laws by simpler objects. And this is something if you think in terms of the classical stochastic control, which I'll come to later, is not unexpected. And this also work by Aditya and his students, which take the same viewpoint coming from a different angle. So this is something one expects, except that we arrive at it a little differently. Then this is also reasonable, natural rather. You propose achieving this approximate conditional law by recursive computation. So it is a notion of recursively computable bits of statistics, which again motivated by partially of the Markovian process, the way they are handled in classical stochastic control by going to the process of conditional laws. And then there's a scheme proposed based on inspired by variational encoders. I'll mention it, but yeah, as I said, I mean, before I started this talk, I was talking to Shuang. I mentioned that I think Aditya asked me about students. I don't have PhD students. I was doing this with these two names I mentioned on the first slide who graduated and left. So this part is kind of left hanging. The computational part is left hanging. So there are some two very tame examples at the end, but I hope to again get some further work done on this front. Okay, so basically, as I said already, that I want to connect the reinforcement learning and classical stochastic control. Of course, it is already connected, but a little more for the partially observed case. And also highlight kind of philosophical connection with what's called internal model principle. It's just an interpretation. The internal model principle in deterministic control has a precise technical meaning. I don't go that far, but it's just using it as an analogy to motivate a certain viewpoint. Perhaps there's more, I mean, I said that it does have something more than just a philosophical idea in deterministic control. Perhaps one can get there in the stochastic control also, but right now, at least this is a pure analogy. Okay, so let me define what was the curse of non-Markovianity. So of course, one knows that in reinforcement learning, there's this curse of dimensionality. Then I also saw someone call the lack of model knowledge the curse of modeling. So why not one more? So the problem that the possibility that the underlying process may be non-Markov is what we call the curse of non-Markovianity. And the idea is to pinpoint what trouble it causes. So again, going back, this is the recursive dynamics of the agent state. We assume that this is stationary. Actually, asymptotically stationary will do, but let's stick to stationary. And this is some notation. The probability that the next observation belongs to some A given the past I denote by small p, where these probabilities are assumed to be continuously dependent on the conditioning past observations and past control. And yeah, so I already mentioned that these are finite spaces, but I also use this notation small s and small u for the cardinalities of the state and excess forces. So this is the reward which depends on observation of n plus 1 and control of n at time n, and r bar I comma u is the conditional expectation of this reward given Sn equal to I, as the agent state being I and the current control being u. So R bar IU looks like what one would desire for a Markovian situation. There's something depending on current state and current control. But in reality, it may not be. And I'm just using this as a kind of simplification or some surrogate object for the actual reward, which depends on the entire. Also assume a stationary randomized policy that the conditional of UN given the past history of the agent state, the observations, and past controls. And I call and assume that depends. So this is kind of a post, and of course controls who choose it. So it's a post Markovian structure here. So assume that it depends only on the current agent state. Okay. Then with this in place, so I have this surrogate reward depending on the current state and current action, and this what would have been a stationary randomized Markov policy in a control case, in a Markovian case, and with that in my hands, I just plug in the usual Q-learning algorithm, ignoring the non-Markovian. See what happens. So this is the algorithm.
Sorry, yeah. Can I ask just a clarification here?
Yeah, sure.
Are you assuming the R bar reward is stationary, or that would in general depend on n?
No, it's stationary. So I assume that the whole processes, all the processes are stationary.
But so this would still be, this is now filtering, right? Because we're looking at the conditional observation history conditioned on the state. So
all the processes are jointly stationary. So they are evolving from minus infinity.
Okay.
The whole ensemble is stationary.
Okay, right. Thanks.
Okay, I'll try to say that later, but if it is not stationary, I mean, if you don't start with a stationary situation, these things will be a kind of over this will probably be harder, but even the transition probability, these things you'll have to impose as assumptions.
Mm-hmm. Yeah. Okay.
So you have this Q-learning algorithm, this is a usual Q-learning, synchronous Q-learning algorithm, indicator SN. So you, when the current state is I and current action is U, you get the I comma UX component using this update rule. So this, of course, I've plugged in the actual reward here. And yeah, so the rest is, so this is what you observe. And then I also define the small q of S prime given S comma U is probability Sn plus 1 is S prime given Sn is I and U. So this is again kind of the control transition probability if Sn were a control Markovian, which it need not be. Again, so as I say, the absence of explicit time dependence of Q is due to our stationary hypothesis. Let phi On O sub n U sub n and phi delta Sn UN the stationary distributions of the stationary laws of these two objects, the entire course of history and the current agent stated current. So delta is the kind of just time at something at time n, and pi is for the full thing up to time. And important observation is this is what actually helps us. This is the key point. Stationary law phi of Sn comma Un is also the stationary law of S cross U valued Markov chain governed by control transition kernel small q, which I defined right here, and control Markov policy. The stationary randomized policy. That's because just consider Sn comma un and Sn plus comma un plus 1. The conditional of Sn plus 1 comma un plus 1 given Sn is precisely what I have said. But stationarity is consistent with the model. So so that's why that helps in what I'm about to say. So in particular, I can write this corresponding parameterized Poisson equation. So if you x will appear as a parameter, and I comma u is the spaces in which Sn and Un take values, and this is the standard Poisson equation where f is the vectorized form of this object, S comma Vth component is all this. This is what you expect after conditioning in the pure learning algorithm. Anyway, we'll see what it does to the analysis of algorithm, what role it plays. But basically, keep in mind that there's a parameterized Poisson equation in the background. So X is a surrogate for Q. I don't know, actually, maybe I should have included something about stochastic approximation with Markov noise. So I'm going to treat this as a stochastic approximation with Markov noise. So where you have, so if you have Xn plus 1, the canonical stochastic approximation scheme is Xn plus 1 is Xn times plus An times such h of Xn plus Mn plus 1, where Mn plus 1 is the martingale difference noise. So this is the standard way of analyzing this. But instead of h of Xn, you can also have h of Xn comma Yn, where Yn is a parameterized Markov chain in the sense that probability of Yn plus 1 being j, given the past is some small p sub Xn of probability of Yn plus 1 equal to j given Yn. So it's Markovian, except that the kind of Markovian, except that the transition probabilities are modulated by the iterates. So that's where this parameter x comes. So it's kind of placeholder for q when I apply this finally. So if you ignore that, it's a usual. For fixed x is it's a standard Poisson equation. Any questions? Again, I don't know familiarity of the audience with this. So it's basically the best way to think of it is if you fix a policy in the average cost MDP, this is the dynamic programming equation, no minimization except for the additional parameter. If f is the running cost, and this is the expected value of the cost under the policy chosen, v is the value function, and this is the linear equation because of fixed policy. It's a standard way of converting basically anything about sums of functions for Markov chains to the corresponding problem for martingales and vice versa. The way it helps is that you can prove things like limit theorems for functions of Markov chains from limit theorems for martingales, basically, which are already around. So you just plug this in and you get. For example, central limit theorem for functions of Markov chains just pops out of central limit theorem for martingales. So anyway, I'll mention wherever it appears, I just pointed out. Now this Qn plus 1, maybe I'll let me backtrack. Remember that this is the standard Q learning algorithm. The previous Q plus the indicator that current state is I at point considerable 3 times the step size, multiplying this observed reward plus gamma max over here. Okay, so maximizing the problem, and Q is equal to minus this. So what the difference is that when you analyze, you add and subtract the conditional expectation of this, which is a standard way. So I do that. Is a multi-step conditional expectation of that. But the conditional expectation with respect to the transition kernel of the imaginary Markov chain, where the process is not Markovian, and then I collect all the problem terms here. So in the standard analysis of Q learning as stochastic approximation, there would be a genuine transition kernel of the process. And once I add and subtract this term, what I would have is gamma times sum over j of max a qn xn plus 1 comma a minus this term added it. there's a martingale difference sequence. So it gives this particular noise. Now this is, and okay, there's another, because Markov is there's some additional martingale different terms come together corresponding also, they're all collected here. This is some noise which comes out of bookkeeping, some kind of asymptotically negligible terms. Okay, I said it here, epsilon n is some asymptotically vanishing random bounded sequence arising from the Poisson equation. And so here I have this parameter x. So the way you, I already said that you can you convert problems involving function of Markov chains to martingale difference sequences. But basically, if there's no x, I would plug in say x and un, then there will be f of x and un minus its stationary expectation times conditional expectation, one step conditional expectation. So once you add these things over n, then the difference of this and this gives you kind of sum of martingale difference sequences. That's the way it goes. Now you have this extra baggage of the parameter x, which is when you apply this here, you will replace it by qn. So here is your Sn un and you have this qn, and qn is actually something incremental. So when you go from n to n plus 1 and apply the Poisson equation trick, you would have Sn un here, you go on to Sn plus 1, un plus 1, that's the standard way you apply this. But then your q is also moving from qn to qn plus 1. But that's a small incremental thing in the sense that that difference of qn plus 1 and qn is of order n. So that's what that contributes to this this epsilon. There's something that, I mean, if you I realize it's kind of unreasonable to spew this out at such a high rate, but it would be a real, it's not very profound, but real nuisance to write down all the steps. Just believe me, it's a lot of bookkeeping basically. Just add and subtract many terms and then pair them together so that you can bound them and whatnot, and you get a lot of stuff which you know is going to zero anyway. And that's what this is. So and psi zeta n plus 1 is the new troublemaker. That's what you get out of non-Markovian. So I'm going to sort of explicitly explain, write down what they are very soon. So n plus 1 is this. This gamma times this, the term which was there in the right-hand side of the Q learning algorithm, minus the one-step conditional expression given the entire path. Okay, so this is not small q of whatever, which I have in my previous expression. So here I have this. This is a one-step conditional expression, but here I have conditional expression given the entire path. So this minus this is a martingale difference. Similarly, here a conditional expression given the entire path. So this is also martingale difference. And this comes out of the Poisson equation. This minus this is also martingale difference. So this together, so there are three. Basically, take adding and subtracting one-step conditional expectations. You get these three martingale difference terms. You collect together into elements. But once you have something which is just martingale difference, the classical stochastic approximation analysis tells you how to handle it. So that is not a problem. Now, zeta n plus 1 is actually compensating for the fact that you took conditional expression in the algorithm. You are not taking, the way I wrote it, I did not take conditional expectation with respect to the entire path, but just one step. So it's the difference between this object and this. Similarly, this object and R bar, which is just a one-step conditional expectation, and similarly for the value function appearing the Poisson equation. So this is the offset due to non-Markovianity. So if it was Markov, all these things would drop out. Okay, because this dependence on if Sn un was Markov, basically one would get so just Sn un. So the important thing is that the conditional expectations of the same object with respect to two different conditioning of events or a conditioning random variable. So these are, each of these is zero mean. When they're stationary, they are all zero mean. Okay, they're basically each pair. For example, this is the middle one. It's the conditional expression of the observed reward given past, entire past, and the conditional expression of observed reward given Sn. So expectation of this difference is zero, the stationary expectation. So that's the part which we'll use. And of course, as I mentioned, this is the nuisance term epsilon n, which comes out of just detailed keeping. But it's something, it's a collection of terms which are asymptotically vanishing, so they don't affect the analysis itself. Okay, so this some terminology. Probably I should spend too much time on it. There's some tech we needed. Say basically, this is based on a previous paper with the same two students, which will appear or probably has appeared in stochastic systems. So this one particular concentration kind of inequality we give, not a classical one, but a little different. I'll soon show you. And this is a notation I need to state that. So dkn is basically essentially the sum of m from k to n. These are assorted things which appear in that formula. So this delta n, the important thing about delta n is that some weighted sum of the zeta, which is the error due to non-Markovianity. And suppose Q star is the unique solution to the target Q value dynamic programming equation, which which would be a legitimate equation if it were a controlled Markov chain, which it is not. If Sn un was a pair of control and state action sequence for a controlled Markov chain. Then the important thing is that Qn does converge to Q star, surely. And this is the error bound. So the first thing is a sort of, it's simple. I mean, just a dependence on the, so I start from some n naught onwards, tell you why. So there is, from some n naught onwards, I can make this statement. So dependence on Q n naught slowly decays, which is not surprising, that to be expected. And delta is some small number I choose, and then this is the second error term. That is small with high probability, which depends on delta. This is a high probability bound. And delta n, capital delta n, so if you remove delta n from this expression, this is exactly the result we have in the paper I mentioned, stochastic system. So what's new is delta n. Okay. So the first two, see, I'm kind of brushing this under the carpet because this one knows how to show this or how to arrive at such things. So these are my initial time is n naught. So this is decaying dependence of the initial condition, and this is some small term, which is small bound for the remainder, which or rather something which is small with a high probability. Okay, there's some various constants, and this is the paper. And the extra stuff is the delta n, which is something new we're stuck with. This I already said earlier. So the first term anyway goes to 0. The second can be made arbitrarily small by, of course, paying a price in the probability. And this is the troublesome term, delta n, you don't know how. And there's no obvious concentration bound. It should be possible, I think, but so far I don't have it. One will have to impose some mixing. Just stationarity, of course, too weak as mentioned, but one will need some mixing kind of hypothesis on top of it to get it. But even otherwise, since one knows that the other two are quite good, but here, if it's not some fast mixing or something, then it can be the bottleneck in the sense that the term which actually spoils the error bound. So what it suggests, so this was basically this term delta n involved the differences between conditional expression with the whole past and conditional expression with Sn comma n. So this motivates kind of philosophy for designing Sn, the agent state Sn, namely to get to improve on the approximation of those conditional laws. So that's where we propose this recursively computable approximate sufficient statistics. And the objective is to try to reduce delta n as much as possible. So yeah, so the conditional law of Sn plus 1 On plus 1 given the whole part should be well approximated by this conditional law given similarly. So the most generally, I would finally don't use this generality, but in principle, one could use a general formulation that you look for something which is a function of Zn, which is recursively computed. But the way the Ben-Conroy model is basically this is an identity map, and there's no extra operation, but one could in principle allow for some slight generality. So some recursively computed object and some function there. But here that latter function is just identity. Okay, then here some minor issues. You can argue that the transition probability function can be uniformly approximated by some finite array objects. So it's basically just some kind of Stone-Wash kind of. Not very significant. Yes, I already mentioned. So what's left is that I want to draw parallel with the POMDPs. So POMDP, just to recall, is a Markov chain along with an observation process. You have the kernel P prime, which in the state I with control U, which gives you a probability of going to state J with observation 4. So that's the classical formulation. And the control is allowed to depend only on past controls and past observations. So the done thing is to write this recursive equation for conditional law. So this is just simple Bayes rule. And then mine ends up being the probability vector values Markov chain, controlled Markov chain. So you sort of convert the partially observed control problem to fully observed control problem in a sense. It's called a separated control problem. Except that the state space has jumped from a finite set to a probability simplex. So you lose in terms of complexity, but it's now fully observed. This is a classical approach. So this is again kind of recursive controlled dynamics. And you can think of approximating this dynamics. And this kind of approach is not new. It's probably elsewhere also, but I am familiar with this particular paper from 2008 by JDU and Borsikas, where they consider finite state controllers and show that if you get more and more complex finite state controllers, you can get close to optimality. Now, the problem for us is that if you just write that n is not the control Markov. That is because if you just look at this recursion, it's driven by the observation. It's not an independent noise. Driven by the observation, and what helps in the classical setup is the conditional law of the next observation given the past also depends only on pi. But that's not the case if the underlying process is not Markov. So that's what that's the crux of the curse of non-Markovianity. And yeah, so the interesting thing is that the classical Q learning algorithm converges anyway, but to the Q star, which is not necessarily the desired limit. And okay, this I will just probably case. I think I'm slightly running short of time. I'll skip some of this and get. So basically, all that is a prelude to this slide. So just one much older result of Singh, Yapolo, and Jordan, and some similar work by Conroy also around the same time. And what they do is they analyze what happens if you aggregate state space. So once you are taking some kind of discrete approximation or something, it's essentially like an aggregation which is compatible with your recursion. And then they have a formula for everything finite setup. There's a formula for what Q you get in the limit. And this one can show that this is actually this. If you map our framework to this, except that our partitions and sets are not finite, but it's essentially the counterpart of this. there's some consistency check. If you look at this thing, Yapala Jordan, for sort of aggregated states, they characterize the limit. And what we have is essentially of the same form in a somewhat more abstract. Okay, so another view, this we do use somewhere. So one can trivially consider the entire past as a control Markov chain. So the transition being done by the shift operator. So each time you just update the last, add O sub n plus 1 and do something to it. And if you observe just time n O sub n plus 1 and U sub n at time n, then it's like a hidden Markov kind of process or a function for Markov. So there's a trivial way of converting anything to a hidden Markov model. It doesn't help much. But in our case, we can use it to show that delta n will actually go to 0 in that result which I mentioned uses this fact. That error due to non-Markovian does go to 0, which those who are familiar with stochastic approximation literature won't find it surprising, because it's known that the reasonable conditions, stationary noise with 0 mean, you can you can consider stochastic approximation with martingale difference noise or Markov noise. These two I already mentioned. In Kushner-Ginn book, you'll also find stationary 0 mean noise considered. So there is just a special case of that. So we know it will go to 0, but that's how you get that result. But we don't know at what rate and so on. That's one of the things. And also the limit is not, it's a different limit, but that's a separate story. And we are kind of living with it. But we are also worried whether we can get a good bound on this noise as we could for the other kind of noise. And so far we don't. Here I just mentioned in passing the analogy with internal model principle. There's a verbal statement, I won't go beyond that. We say that a good controller incorporates a model of the dynamics that generates the signals which the control system is intended to track. So the viewpoint I want to take is that the filter, the nonlinear filter or any approximate filter is actually a model you carry in your mind or implement to control the original system. And the better the model, of course, we will control it better, but of course, there's computational trade-offs. So in case of Kalman filter, I guess the analogy is more convincing, and the Kalman filter dynamics does look like the original system. But I feel there's kind of something more general one should keep in mind in approaching. In particular, I feel that when you use neural networks and so on, it makes better sense to use a recurrent neural network. Okay, so one natural choice is, of course, a finite window, and this, I think, Seder is in the audience. So this has already been analyzed very nicely by Gitara and Excel. This is another relevant reference, and as I already mentioned, there's something close in the formulation by Subramanian, Siraj, and Morgan. So these are the two related works I know. There could be more. Perhaps if you can find out better. And let me come to this last step. So I once attended a talk by Steve Brenton and then looked at some of his work, and I found that approach interesting that you kind of, they use variational autoencoders, but we change it a bit. The idea is, okay, let me go to the picture. So where it's, this is the, go back. So we have two neural networks, a state neural network, which takes the current state, current control, current observation, and outputs the next state. So this is a model for dynamics. So this is what Brenton et al. Will call encoder. And then they have it's followed by something they call decoder, and they match the output and input. But for us, it's different. So what we call the second neural network an observation neural network, and along with SMCN, we just try to track. I mean, this is not a decoding of the input, but it's a prediction of the next observation. And then you compare the actual observations with you, what you predicted to tune the network. That's the idea. So given time n, you have the state at n minus 1, the control at n minus 1, and the observation you just observed, and you spit out n, Sn. And then the next one basically predicts. You take the output of Sn and UN control UN time n and predicts over n plus 1. And we work with this simple thing. I mean, principle one should compare some distributional kind of errors, a distributional criterion. But we stuck to something simple, and as I said, the operational front we have not gone very far. Yeah, so you compare these two, and basically we stuck to the simplest possible. And one caricature of the opportunistic, first example we took was the caricature of the opportunistic scheduling problem in communications, where the channel varies randomly between, say, good and bad. And you try to, if it's a bad channel, you try to hold back the packets, but then you pay in terms of delays. So there's a relation between delays and queue size. So you take a cost proportional to queue length, and also there's a cost proportional to energy, which depends on the channel state. So you have to optimize. Each time you decide how much to transmit. So there's a standard queuing model for that. And so this observation process something analog. And what does this is small case we found the transmit all strategies, of course, bad. Mindless strategy, and then should have brushed up. Yes, I forget what the other algorithm we compare with. But anyway, this does well. And we also tried on cardboard, which is the deterministic problem. Seems to be the popular thing to try for everything. And we get, there we got a good performance. And basically, except for this occasion spike, which I have seen in other sort of reported experiments also for other algorithms. So basically, it just swings that comes back every now and then. So this was a more promising thing, but I mean, this was hardly enough computational evidence. So hope I have something more to show eventually, depending on how much current support and otherwise I get. Okay, so let me come to feature work, and of course the big problem is non-stationarity. The important thing you lose is everything which I claimed is true will have to be imposed as an assumption. So as Aditya pointed out, the R could be problematic. Then, of course, sorry, general state spaces. So here the life was made simple because everything was finite. So some of the arguments it was quite harmless state space and action space to be with. Other is this a little bit too sensitive for that. Okay. And then better concentration bound. Maybe I forgot to say something about the bounds. Solving concentration bound and the classical concentration bound. So this is the kind of thing I have been doing for a while in other contexts also. But that was motivated by this tapping phenomenon in the economics models for increasing return economics, basically. So there may be, for example, multiple alternative technologies, and one gets just because of networking effect and so on, or sort of all standardization, etc. Something which gets some initial advantage because standard, even if it's not the best possible technology. There are ample examples of that. Or two similar restaurants, everybody ends up going to one of them. Somehow it becomes very fashionable, and the other goes out of business, and so on and so forth. And so there's this issue of stochastic approximation like dynamics, earn models, for example, where you can end up in one of the many possible equilibria. And the problem there is if you are in the domain of attraction of one equilibrium, can you say anything about the probability with which you know that it's high probability you will go there? So can you get some kind of a bound on it? So that's the kind of activity I started with. So what it says is that you have to pick a not large enough. Essentially, you have to ensure that the step size is small enough. That's the main reason. Start with some and not repeater. But so instead of starting as traditional sample complexity bounds, which depend on concentration inequality, you start at time 0 and say something about how close you are to the goal at time n. Here I'm starting at some time in future, but I want to make a statement for all n thereafter. So with the high probability, you remember I can quantify the neighborhood of the goal in which you remain forever. I mean, after n naught with for all n greater than equal to n naught with a high probability. It's a somewhat different kind of bound. And that's the so that I mean, it's a decent bound, but again, I suspect that one can probably improve on that. I think the order is probably not too bad in the sense the exponent. Constants could, I'm sure, can be improved. Okay, so I'll stop here, 50 minutes exactly, and thank you for your attention. There's still time left for questions.
So thanks a lot for the talk.